Welcome to Part 8 on rational functions. We have g of x equals 2x times x minus 3 times 2 plus x all over x minus 3 times x squared minus 16. Factoring this further in the denominator will give me x minus 3 times x plus 4 times x minus 4. Looking for any removable discontinuities, I can divide out my x minus 3. Since there will be a whole at x equals 3, we can find g of 3, and it will give us the y coordinate of the whole. So substituting 3 in for x will give me the following. 2 times 3 times 2 plus 3 all over 3 plus 4 times 3 minus 4. In the numerator, I will have 6 times 5, which is 30. In the denominator, I will have 7 times negative 1, or just negative 7. I'll go ahead and write it as negative 37ths. So the coordinate is 3, negative 37ths. Now let's find any vertical asymptotes. Those will be found at the denominator locations. So we will have x equals negative 4 and x equals positive 4 as the two locations for my vertical asymptotes. The whole in my graph will be at 3 negative 37ths. Now let's see about horizontal asymptotes. We always look at the degree of the numerator and compare it to the degree of the denominator. The degree of the numerator is 2. And the degree of the denominator is 2. Which means that the horizontal asymptote will be at the value of the leading coefficients. Now, don't be the person who looks at the number first in this binomial 2 plus x. Remember, this could be written as x plus 2, therefore, our leading coefficient in the numerator is just 2, and the denominator's leading coefficient is 1. So we will have a horizontal asymptote at y equals 2. This is because the degree of the numerator equals the degree of the denominator. Since we now have a horizontal asymptote, we can check to see where the curve will cross it, if at all. So we'll take the 2x times x plus 2 over x plus 4 times x minus 4, and we will set that equal to the horizontal asymptote value at 2. Multiplying both sides of the equation by x plus 4 times x minus 4 will allow us to reduce the denominator, and we'll have 2x times x plus 2 equals 2 times x plus 4 times x minus 4. I'm going to FOIL these out so that I can combine like terms and set it equal to 0. This will give me 2x squared plus 4x equals 2x squared minus 16 times 2, so 32. Notice that if I subtract my 2x squared from both sides, I'm left with 4x equals negative 32. That means x is equal to negative 8. So there is only one point at which the rational function crosses the horizontal asymptote y equals 2, and that point is at x equals negative 8. The coordinate point for that, by the way, would be -8, 2. Let's next find any roots or zeros of the rational function. That will be at anything that is in the numerator set equal to 0. So I will have roots at x equals -2 and at x equals 0. So these are where the rational function will cross the x-axis. I'm also going to check for where my function will cross the y-axis. These are my y-intercepts. So my y-intercept will be when x equals 0. So this will be 0, 0, because if I put 0 in for x into my original function, the numerator will be 0. So my y-intercept is at 0, 0. Let's look at all the roots. We have 2x, we have x plus 2, we have x plus 4, and x minus 4. So it's a positive degree 4 polynomial to get my signs. I'll have a root at 0, at -2, at -4, and at +4. And I know a degree 4 function will start on the top left, wiggle through the roots, and leave from the top right. So my signs will be positive from -infinity up to -4, and from -2 to 0, and also from 4 to infinity. The only intervals on which the function is negative are from -4 to -2, and from 0 to 4. Now remember, this is only my sign chart. This does not tell me what the graph looks like. So now let's actually graph the thing. I have vertical asymptotes at -1, 2, 3, 4, and -4, and at +4. I have a horizontal asymptote at 2. I have roots at -2 and 0. I have a hole in my graph at 3, -37ths. So right about here. I have a crossover point on my horizontal asymptote at exactly -8, 2. So right about here. And now let's list where my function is going to be positive. Again, it's positive from -infinity to -4, from -2 to 0, and from 4 to infinity, which means the other sections will be negative. I know I have to cross the 2 roots, and I will be positive between those 2 roots. So I'm going to connect those dots with a curve, and then I'm switching to negative, so I must approach this vertical asymptote on the left and also the vertical asymptote on the right. I never cross the horizontal asymptote on the right side of my graph, so this is just a curve approaching both the horizontal and vertical asymptotes. And on the left, I do actually cross the horizontal asymptote. So it'll look something like this, where it goes below, and then it approaches the horizontal asymptote from the lower side, not on the top of it. And this works out because we can see where the function is below the x-axis, where it is above the x-axis. That all falls into place. My y-intercept is at the origin, and my function does not exist where we had a removable discontinuity.